So space-time diagrams, we're going to talk about this to reiterate what we were just talking about for Baran, who's enjoying biology right now. Space-time is a thing. We don't know what it is. As with some other things in physics, like light, we don't really know what it is. If you ask someone what is mass, an advanced physicist will tell you it's an interaction with the Higgs field created by the Higgs boson. That means nothing. We don't know what it is. But we, as with everything we study in physics, we know what it does. So we know we've measured the effects of it. And so space-time, the idea of it is really just in here. It's a three-dimensional fabric of space. I would love to build a model. If anybody can build a three-dimensional model of space-time, I would appreciate that. I'll give you some marks for it. Braun, that's for you. You can build a model. I'd like to see it. Then we can like shove a basketball into the middle of it and see it like stretch. Jordan's on it. You can imagine it as some taut, kind of rubbery strings in all three dimensions. They go vertically, they go sideways, and they go depth-wise. And they have they're taut, but they have a little jiggle in them. And when you shove an object into it, you can think of it as though the space-time is being squished, kind of compressed around the object. Okay. And when you move fast through it, those objects, that space-time changes things. Okay. All right. So Minkowski diagram looks like this. You have time here, and you have space here. Okay, and so time is moving upwards. And when you get into it, this actually becomes CT, but I'm just going to introduce it to you today because I just want you to understand how this works. Let's say, tell me an event, any kind of something that happened.
Kennedy's assassination.
Kennedy's assassination. Okay, so let's put that here. JFK, we'll call it. Okay, and give me a different event at another time in another place.
Jesus was born.
Oh wow. Okay. Well, we're really getting into the history. Let's say Jesus is here in the Middle East. We'll just draw that. Okay, so, something maybe in the future. Oppenheimer, or maybe the atomic bomb.
Yeah, atomic bomb.
Okay, that's okay. If this is West and Middle East, that would be Japan, which would be maybe over here. Let's say. That's the atomic bomb.
Yeah.
This is probably more complex than it should be.
Is it? What? The atomic bomb happened before JFK though.
It did? Oh yeah, right. Thank you. See, physics guy, not history guy. Let's put this here. Actually, these would all be like really like this. And JFK would be like somewhere here, right? I should have said simpler thing. I thought you were gonna be like, I ate breakfast or something like that. Lucas's mind is on the big ones. Okay, so let's pick an event. Let's pick the atomic bomb and say that the interesting thing about a space-time diagram is that it shows how time changes with motion. So as you get faster, so hold your arms up like this. This is, well actually, no, let's do it like this. Hold your arms like this. This is your y-axis and this is your x-axis, okay? I don't know if maybe go like this, that's easier. Now, when you move fast, it's not that, like if you have an event and you're gonna move through space and time, if this is space and this is, or sorry, if this is time and this is space, you guys know it's gonna go like this, right? It's gonna be at an angle. So you just have a train and it's just going along like this at a constant velocity, right? If you go fast enough though, you're gonna see a change in time, right? That's not a change in your motion. That's time itself changing, right? So your axes go like this. Okay, take that in. It's not you changing, it's your axes changing. So if you move fast, this is going to tilt and time will also tilt, okay? And the faster you go, what's gonna happen to those axes? The more they're gonna tilt until they get to, where do you think is 45 degrees?
Speed of light.
Speed of light, good. So your axes are gonna go like this. If you take nothing else out of today, just hold that thought in your mind. As you move faster, this goes like this. Before we get rid of these events, let's say that the atomic bomb happens far away, JFK is over here, this is not to scale. If I shone a light, well this is handy because it did shine a light, I guess. It would go, that light would go out at 45 degrees, right? You agree? Mm-hmm. And if you think of this in terms of, so this is like CNC, and in this diagram, in a Minkowski diagram, time is moving upwards. He did that on purpose. So what is this kind of triangle between C and C? Like this is, we're making this west and this east. So if the light goes out towards the west and it goes out towards the east, what is between those light rays? Yes?
It's the future that can see it.
This is the future. So, could the atomic bomb have influenced JFK's death? Yes. Yes, definitely. Because it is in the future, and we call this a future cone. Because this is actually, if you think about it, space is in 3 dimensions, right? So you can think of a z-axis as well. So this is like, it's like an open ice cream cone. Okay. So that light can go west, east, north, south. It can't, if there was something else that happened, like, let's say on Mars, a robot lands on Mars over here. Could the atomic bomb have affected the robot landing on Mars? No, because it's outside of that future cone, right? But be careful with that one because you'll see that the same time is not the same for everybody. We're gonna see that. Could Jesus being born have affected the atomic bomb? Yep.
Yes.
Could it have affected JFK?
Yes.
Yes. Could JFK being shot have affected the birth of Jesus?
No.
No. Okay, so if that's the future, if you go up 45 this way and that way, what's down here? This is the past. And so you have a past cone as well. And this is a thing that Einstein was very interested in. He was pretty philosophical guy. I think it's because he was Jewish and they, you're interested in, well, we're all interested in that, right? So for a long time, he was deterministic. He would tell people that it doesn't actually matter what you do. Like he would say that, he'd be like, don't worry about it. It doesn't matter. Everything is gonna happen. It doesn't matter if you have toast for breakfast or watermelon slices. That was predetermined already, long time ago. It doesn't matter what choices you make, because the universe is gonna ensure that you make that choice, whether you think about it or not, or whatever, And there was a big argument at a table at a conference, and Oppenheimer and others were like, that doesn't make any sense. Your choices are going to determine the future, and there's a whole bunch of different potential futures, and your future cone can move around if you decide to walk this way or say this or do that. The philosophy behind it is really interesting, but the physics is pretty solid on this, that if you are inside that light cone, that is what you have the influence over. So if you think about your own life right now at this moment, the choices that you make can affect the future, but only the future of something that is within the speed of light from you in the future. Does that make sense? Let's draw another one. Let me just talk a little bit about. Bless you. Okay, let's have some more normal events. Let's say that. Say you have something happens here, Arsha brushes his teeth, something like that, and it's event A, and then you have, let's say, I always bumble this, so I have to try to get it right. Actually, let's put this one close to here. And then let's say event B is here. Okay, that's A, and this is B. So Arsha brushes his teeth and Baran brushes her teeth. Could Arsha brushing his teeth have affected Baran brushing her teeth? No. Is Baran brushing her teeth in the future from Arsha or in the past? In the future. Unless Arsha starts to move fast. And if he's moving fast, then this line changes, right? So he goes like, let's say he's moving fast and he does that. So this would be T prime, and this would be X prime, right? So let's think of, well actually, here's the better way to say it. Let's say we're in a spaceship, we're moving fast, we're flying fast, right? Who wants to be on the ground, not in the spaceship? Anna wants to stay on the ground. She doesn't like rides or. Okay, so Anna is here in reference frame S. She's sitting on the ground and she looks over and she sees Arsha brushing his teeth and then Baran brushing her teeth. Okay, who wants to be in the spaceship? Ilya wants to be in the spaceship. So Ilya, I'm with you, Ilya. I want to be in the spaceship. Ilya is moving fast in S prime. To Ilya, what happens first? Braun brushes her teeth first, and then he sees Arsha brushing his teeth. Okay, so the order of events is not the same for every observer. Does that make sense? Don't forget that when this happens, when Ilya moves fast, it's not just X and Y that move, right? So we think of, like, if this line goes out, here, I'll draw these in green. For us sitting on the ground, Anna's sitting on the ground, she sees Arsha happen here, right? And then Baran happens there, yes? But for, I'll do this in blue. But for Ilya, he's moving, so this line here is like that. Okay, these lines move that way for him. So all of space and all of time, they all shift, right? All these lines, and the vertical ones change too. They're not going straight up. So the graph paper, if you think of a graph paper with a bunch of little hinges at the joints, they all go together. And that's why for Baran, for Ilya in the spaceship, as you move up, you have to think of it like you move through space, or you move through time with a warped space. So we think of it like this, and as we move through time, we see we see Arsha brushing his teeth, and then we see Baran brushing her teeth, and then we go on into the future, right? If you're moving fast, that x-axis goes like this, and this is the past, and this is your future. So if you're in the spaceship, everything is tilted, and you go up and you see Baran brushing her teeth here, and then you see Arsha brushing his teeth, and then you move up into the future like that. Weird. Sure. So normally we don't have these tilted lines. Normally we would have, so there's two things that are weird about this. Normally we have time on the X, right? And we have space on the Y, and as time goes on, we travel a little bit of distance through time. That's just a normal graph. And that's true if you're in reference frame S. And Minkowski said, let's always draw this as the non-moving observer. This is like the proper time and space. But he said, let's flip it so that time is on the Y-axis, just so that instead of time moving side to side, time can move up. So everything is always going from bottom to up, okay? If you're in an inertial reference frame S and you're not moving, time clicks by, goes click, 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 click. You see an event, that's Arsha brushing his teeth, and then you go click, and now you see Baran brushing her teeth, and you go click, 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 click. As the future moves, you move upwards. When you move fast, time itself changes, and what else changes? Space changes as well. Length contracts, right? So you move through space from here, like this. You have to put that angle. When you move fast, your axis, your space and time axes tilt. We have to do this, right? Minkowski had a great idea to show this because there's no other way to show it. You can't just say, well, we'll keep the graph paper the same, but we'll just make it really steep or something. That's just moving faster through a normal space-time, right? The only way to show it is to show that space and time themselves tilt. You're not moving faster, you're not slowing down. The time and space around you is changing. So we have to take this normal line that you've always known, and we have to tilt it up. And now we tick through the future this way. So we're ticking through the future and we go bang. I actually see Baran brushing her teeth first. And then I see Arsha brushing his teeth. And then I move on like this, right? From the spaceship's perspective, could Baran have caused Arsha to brush his teeth?
Yes.
Yeah, could have. Where would she have to be so she couldn't affect him?
Below him,
Where and when?
45-degree angle above him with his speed of light.
Yeah, alright.
I understand this.
Okay.
I just have one question.
I don't.
What happens to the other quadrants when the axis tilts?
That's a good question. So, I mean, it looks the same, but we generally say this is where you're looking from in reference frame S. And so we generally have it here, and but this one does go like that. These axes keep going, and you can draw it, but it's a bit weird because these ones you would draw like this,
Yeah.
right? It's a little, it's just weird.
Yes.
But you can have an event over here. And that event, wait a minute, I'm thinking. I think that event is the same. You actually don't, I said that wrong. You don't tilt these ones. You tilt those ones because it depends which direction you're moving in, right?
Makes sense.
Yeah, this one is moving that way. So we tilt the axes in that direction. But you would still go up. You'd still go up in the future like this. You hit Baran and then you hit Arsha and then you hit that one, right? Even though to us, if we're going normally on the ground, you see like Arsha and then the other one and then Baran, right? I'm second guessing myself here. Could Baran have caused Arsha? I don't think so, actually. Tell me why.
It's not 45 degrees.
In this, if this is to scale, could either of them have caused each other? No. So to the spaceship, she happens first and then he happens. To us, he happens first and then she happens, but neither could have caused the other. I'm realizing I said a mistake. I'm sorry, bro. Hopefully you watched the whole video. Why could this one not have caused that one and that one not have caused this one? Yes?
They're not in each other's future cones.
Yeah, they're not in each other's light cones. So you can only go 45, right? Why can you only go 45?
Because the speed of light.
The speed of light. That's right. Yeah. You can keep contracting and dilating time, but only to the speed of light. So even if she sends a message at the speed of light, Arsha, the soonest that he can get that message is right here. Does that make sense? If she sends a message and he moves at the speed of light, he will only get it there. So her event cannot cause his event. When the two happen is, the order of the events is determinant on your speed. By the way, this has been proven. When they were orbiting in the space shuttle, you could see, you know how when you're in space, you can look down, you see the clouds on the Earth, and you can see lightning strikes from above? This was observed where the lightning strikes were being recorded on the ground and in the space shuttle, and two lightning strikes that happened at identical time from the space shuttle were recorded on the ground as happening at different times. So there is like an effect there. Yeah, Ursha.
What if like event A is also moving? Then what happens to the light company?
Well, so we generally don't do that because you'd have to put this you'd have to make another axis, right? Like you would draw this, but you would put event A here then.
Oh.
Yeah. Yes.
So I'm assuming that space is 3D. How are we summarizing it in one dimension?
Well, because paper is flat. So, and Mikowski didn't have a three-dimensional model. He just wanted to be able to draw it quickly, right? So that's why we're doing it. But yeah, you can think of these as cones, right? That's why I drew this. Like that's the top of the cone, and this is the top of this cone. Does that make sense? So really, in truth, you can obviously move forward and back, and there really would be another axis like this, and this would be y, and or this would be like x and z and y, but it's opposite to what you think of it, right?
Yeah.
You think of x and y and z going up, but everything's tilted because we wanted to have time going forward. But yes, it is three-dimensional for sure. We will talk more about this. I just wanted to show it to you. This is a bit of a mind bender. Think about how you would, by the way, there's a little terminology. If you have an event, let's say that this stays still, it will have a line into its future. That's called the world line of the object. The object has a world line. I don't know why they call it that, but. And so if you have something that's moving, the world line will tilt, obviously, but that's where it is in reference frame S or whatever. I think that's pretty good intro to space-time diagrams. It takes a little while to think, so I'm not gonna give you problems on it today. I just want you to think about it. If you're like, I need to know more, go into the SOCOS and read the second section of the relativity. Did I post the relativity stuff for you? I posted something. You asked me to post a bunch of stuff. I did some of it. I'll post the SOCOS relativity stuff today, right now, so that you have it. So you can look through that. But I honestly, my recommendation is don't. In fact, I'm going to ask you to do something. Everybody put your eyes on me. What I just told you, I want you to do something with it. I want you to forget it. Okay, I don't tell students this often, but I just want you to forget this for now. We'll bring it up next day. But the trouble with thinking about it is that it's in here, right? If you keep it in here, this guy wants to get at it. Your subconscious mind wants to get at that and put it somewhere. And if you keep thinking about it, just quit thinking about it. Let me put this somewhere. By the way, you want to know where students put this stuff? We don't have a place for it, right? Because ancient humans, we never moved fast, so time was always the same. Length was always constant. You have zero use for this, right? So when you learn special relativity, most people put it in the place where we store sentence structure. Isn't that interesting? Like, not words, but the structure of sentences, like subject, noun, verb, that kind of thing. I think it's because like you have to understand the difference between a verb, which is something doing, right? It's doing, whereas it's happening over time. Whereas a noun is like, it's there and it doesn't change. So the difference between those two things is interesting. So that's where you keep it. So you can think about sentences if you want. But don't think about this, just forget about it. I'm gonna give you some relativistic addition of velocities problems.